Hi guys, in this tutorial we're going to take a look at the ideal gas law. This is basically an equation, one of them that you really just should take the time to memorize. A lot of times I tell you that if you don't have to memorize, then why bother? But in this case, here's an equation that is derived theoretically and is used so often that it's just worth committing to memory. So let's take a look at it. The equation is PV equals nRT. P in this equation stands for the pressure, usually measured in either atmospheres or kPa. V is the volume, measured in liters. N is the number of moles of the gas you have, measured in moles. R is called the ideal gas constant. Its value varies depending upon the pressure that you use. If you're in atmospheres, the pressure is 0.0821. If you're in kPa, then the value of R is 8.31. Finally, T is the temperature, and that, as always, has to be measured in Kelvin. All right, let's take a look at a sample problem using the ideal gas law. So let's suppose that we have some helium gas, and it's at a pressure of 500 millimeters of mercury. It's at a temperature of 25 degrees. We have 12 grams of the helium, and we're going to try to calculate the volume of that. Well, first of all, we have to convert our measurements to units that are appropriate for the equation. So we're going to convert millimeters of mercury to atmospheres, and we're going to convert the temperature to Kelvin. And finally, we need to convert that mass into moles by dividing by the molar mass of the helium, giving us 3 moles. Now, all you got to do is plug and chug. You're going to just plug your numbers into the ideal gas equation, and in this case, we get that the volume is about 111.5 liters. Okay. So here's another important number or calculation we can do with the ideal gas law, and that is to calculate the volume of 1 mole of a gas at STP. And STP, if you recall, stands for the standard temperature and pressure of a gas. That's 0 degrees and 1 atmosphere of pressure. Now, the ideal gas law, being ideal, assumes that all gases behave the same. So it's assumed that all gases would have the same volume if they had the same number of particles and if they're at the same temperature and pressure. This is a result of Avogadro's principle, basically. So let's take a look at this. So again, standard temperature and pressure, 0 degrees C and 1 atmosphere of pressure. So if we find the volume of 1 mole of a gas at these conditions, we get an interesting number, 22.4 liters per mole. Again, this represents the volume of 1 mole of a gas at standard temperature and pressure. And this is a number that we can use to do a number of calculations, such as calculating the density of a gas at STP. Now, because gases and their volumes are affected by the temperature, pressure, and so forth, recording something like the density of gases wouldn't have a whole lot of meaning unless we all did them at the same conditions. So scientists agree that when recording the accepted values for the densities of gases, that we're going to do it at STP. So that we know what we're comparing here, okay? So this makes for a really easy calculation, one that you should all get right on your next test. We can calculate the density of anything by using the equation mass divided by volume. In this case, we know or can use the volume of 1 mole of a gas at STP is 22.4. And so we have to divide that into the corresponding mass of 1 mole, which is, of course, the molar mass of the substance. So, for example, suppose we're going to try to find the density of carbon dioxide at STP. all you need to do is find the molar mass of the carbon dioxide, 44, and divide it by 22.4 liters per mole, and we get that the accepted theoretical value for the density of carbon dioxide at STP is about 1.96 grams per liter. All right, so now we're getting into some fancier calculations using the ideal gas law. We can use it, for example, to calculate the density of a known substance like methane at any particular temperature and pressure. So let's suppose we have some methane that's at -5 degrees and it's at a pressure of 68 kPa, and we're going to calculate the density of the gas at those conditions. So first of all, we have to convert the temperature to Kelvin, and then we're just going to plug into the equations. In this case, we know that density is mass divided by volume. And in order to have a mass, in this case, we're going to use the molar mass of the methane. So notice that you need to know the formula for methane, CH4, so that you can look at the periodic table to get the molar mass, which is 16 grams per mole. Now you can't divide this by the 22.4 because that's only at STP. We actually have to calculate the volume of the gas at these conditions, and for that we can again use the ideal gas law. The trick here is, and the thing that a lot of students forget, is to put in the number 1 for the number of moles. Since in the density equation we put the mass of 1 mole of the methane, we need to put 1 in for N, the number of moles. This gives us a volume of 32.7 liters. Now we just need to divide that into the 16 grams per mole, and this is giving us a density of 0.489 grams per liter. Again, I can't tell you how many times students get frustrated on this one because they just don't know what to put in for N. You got to think about this one a little bit because it's not going to be given to you. You have to remember that the molar mass is per 1 mole. All right. Here's another very important use of the ideal gas law, and that's to calculate the molar mass of an unknown gas. And this is really at the heart of what chemists do. Very often they're trying to determine an unknown substance and what it is. And determining the molar mass of a substance is probably the most important thing you could probably figure out for a compound. So let's take a look at how that's done. It's really pretty similar to the problem that we just looked at. So in this case, we know the mass of a gas, we know the volume of a gas, and we know the temperature of a gas, and we also can record the pressure of a gas. And from these pieces of information, we can get the molar mass. If we recall that basically the molar mass of anything is the grams per mole. In other words, it's the mass divided by the moles. And in this case, we know the mass, which is 1.04 grams. What we need to determine here, in this case, is N, the number of moles. And we're going to use, again, the ideal gas law to determine N. And so, again, just making sure that all of your numbers are in the appropriate units, plugging into the equation, gives you 0.0133 moles of this gas. Now we're just going to divide that into the 1.04, and that will give us the molar mass of this substance to be about 78 grams per mole. This technique of determining the molar mass of a substance was first done by Dumas, and so is often referred to the Dumas method of calculating the molar mass. Now, this doesn't actually give us the formula for the compound. However, it is possible to do experiments like you've done in class to determine the empirical formula of a substance. And remember that the empirical formula is the simplest whole number ratio of the elements in a compound. So let's suppose that you did an experiment that determined that for this gas, this unknown gas, the empirical formula was CH. And the question is, all right, well, what's the actual formula? We know that this compound has a molar mass of 78. And if the actual formula was CH, it would have a molar mass of 13. So if you divide 78 by 13, you find that it goes 6 times, and therefore the actual molecular formula here would be C6H6. Okay, so hopefully this is helpful. You're guaranteed to have these kinds of problems on your upcoming test, so study them well and practice them many times. And the more you do that, the better and quicker you'll be at these kinds of problems. Good luck.